Hello friends, welcome to the lecture on solution of homogeneous linear system with constant coefficients. Let us consider the vector differential equation x dot equal to Ax. In what follows, we will reduce the problem of finding all solutions of this vector differential equation to solving the system of homogeneous system of equations Ax equal to B. The eigenvalue eigenvector method we are going to discuss to find all solutions of the vector differential equation x dot equal to Ax. So, let us consider the first order linear homogeneous differential equation 1, which is x dot equal to Ax. Our aim is to determine n linearly independent solutions of this vector differential equation. Now, we know that first order and second order linear homogeneous scalar equations have exponential functions as solution. For example, you consider the first order linear homogeneous scalar equation, then it is dx by dt equal to some constant times x, okay, which we can write as dx by dt dx by x equal to a dt, and which gives us ln x equal to a t plus some constant which we can write as ln c. So, then x is equal to c times e to the power a t. Same is the situation when you consider second order linear homogeneous scalar equation d square x by dt square plus some constant say alpha times dx by dt plus beta times x equal to 0. So, we have exponential functions as solutions of these first order and second order homogeneous scalar equations. Therefore, what we do is we consider x t equal to e to the power lambda t into v, where v is a constant vector, and take it to be a solution of equation 1. Now, let us see that when you when you put e to the power lambda t into v in the equation 1, we have on the left side dx by dt. So, d over dt of e to the power lambda t into b gives you lambda times e to the power lambda t into b. This is because e to the power lambda t we know is equal to some is equal to 1 plus lambda t plus lambda square t square by 2 factorial lambda cube t cube by 3 factorial and so on. So, when you differentiate this with respect to t, what you will get is d over dt of e to the power lambda t will give you lambda plus 2 lambda square t by 2 factorial, okay. So, we will get lambda square t, and then we will get 3 lambda cube t square by 3 factorial. So, we will get lambda cube t square by 2 factorial and so on, which is equal to lambda times 1 plus lambda t plus lambda square t square by 2 factorial and so on, and so it is lambda times e to the power lambda t. So, when you differentiate e to the power lambda t into v with respect to t, where v is a constant vector, what we get is lambda e to the power lambda t into b, and by the matrix properties, e to the a matrix, A is a constant matrix, A is a matrix into e to the power lambda t into v, e to the power lambda t is a scalar quantity into v will give you e to the power lambda t into a b. So, what we will get if you put it in this equation 1 x t equal to e to the power lambda t into v, what we get is we get the following. We get okay. So, we get lambda e raised to the power lambda t into v equal to lambda e to the power lambda t into v equal to e to the power lambda t into a b. This is what we get. Now, e to the power lambda t is never 0 for any value of t, okay. So, we can divide this equation by e to the power lambda t and we get lambda b equal to a b. So, x t equal to e to the power lambda t into v will be a solution of equation 1 if and only if we have this equation lambda into e to the power lambda t into b equal to e to the power lambda t into a b, which gives us a b equal to lambda v. Thus, x t equal to e to the power lambda t into v is a solution of the equation 1 if and only if lambda and v satisfy a b equal to lambda v. Now, a non-zero vector v satisfying this equation a b equal to lambda v is called an eigenvector of the matrix A with eigenvalue lambda. Now, here the case v equal to 0 is excluded because it is an uninteresting case. You can see that a b have a b equal to lambda b. If you allow v to be 0 vector, then a into 0 vector equal to lambda into 0 is true for any scalar lambda. So, we discard this case, and so the vector v equal to 0 is not allowed to be an eigenvector. So, we will say that a non-zero vector v which satisfies a b equal to lambda b will be an eigenvector of A associated with the eigenvalue lambda. To find the eigenvectors of A, we rewrite the equation a b equal to lambda b as, now when you have a b equal to lambda v, we have a minus lambda I b equal to 0. Now, remember we always write a minus lambda I because we cannot subtract a scalar lambda from A. So, we multiply lambda by identity matrix of the same order as A. Okay. So, a minus lambda I into b equal to 0, this is what we get. Now, this equation has a non-zero solution only if determinant of a minus lambda I equal to 0. So, determinant of a minus lambda I must be 0, because if determinant of a minus lambda is non-zero, then a minus lambda I inverse will exist, and you can pre-multiply this equation a minus lambda I b equal to 0 by a minus lambda I inverse, and what you will get b equal to 0, but b is not equal to 0. So, a minus lambda I into b equal to 0 will give us a non-zero solution only when determinant of a minus lambda I equal to 0. Hence, the eigenvalues lambda of A are the roots of the characteristic equation determinant of a minus lambda I equal to 0. If you expand this equation determinant a minus lambda I equal to 0, what you get is this determinant a11 minus lambda a12, that is from the matrix A, the diagonal elements of the matrix A are subtracted by lambda. We are subtracting a from A lambda times identity matrix of order n. So, this is what you get. So, determinant of this equal to 0 gives us a polynomial equation in lambda of degree n. The eigenvectors of A and the eigenvectors of A are then the non-zero solutions of. So, once you find the values of lambda which satisfy this characteristic equation, the corresponding eigenvectors are given by the non-zero solutions of the equation a minus lambda I b equal to 0. Now, the determinant of the matrix a minus lambda I is clearly a polynomial in lambda of degree n, with the leading coefficient will be minus 1 to the power n lambda to the power n. Now, this polynomial is called the characteristic polynomial. Determinant of a minus lambda I is called the characteristic polynomial of A and be denoted by p lambda. So, p lambda is equal to determinant of a minus lambda I. For each root lambda j of p lambda, there exists at least one non-zero vector vj such that a vj equal to lambda j bj. Suppose there is a value of lambda, say lambda j, for which p lambda is 0, that is p lambda j equal to 0, then the corresponding non-zero eigenvector will be given by a bj equal to lambda j bj, or you can say a minus lambda j I bj equal to 0. So, from here we will get at least one non-zero eigenvector corresponding to lambda j. Since p lambda has at most n distinct roots, p lambda being a polynomial in lambda of degree n, so it has at most n distinct roots. Every n by n matrix has at most n eigenvalues. Finally, since the space of eigenvectors V equal to b1, b2, bn, it has got n components. So, the space of vectors has n dimension n, and therefore, every n by n matrix has n linearly independent eigenvectors at the most. Now, if V is an eigenvector of A with eigenvalue lambda, then C into V, where C is not equal to 0, is also an eigenvector of A with the same eigenvalue. So, this is very simple to see. Suppose lambda is an eigenvalue of A and B is the corresponding eigenvector, then we have AB equal to lambda B. Now, let us see A C B C is a scalar which is non-zero, we can write it as C times AB by the matrix properties. So, this is C times lambda B. So, we have this is equal to lambda times CB. So, we have ACB equal to lambda times CB. So, if V is an eigenvector of A corresponding to the eigenvalue lambda, then CV, where C is non-zero, C is taken to be non-zero because if you allow C to be 0, CV will be a 0 vector. So, it cannot be an eigenvector. So, C is not equal to 0, then if you take, then CV is also an eigenvector of A with the same eigenvalue lambda. Now, for each eigenvector Bj of A with eigenvalue lambda j, xj t equal to e to the power lambda t lambda jt into Vj is the solution of 1. We have seen that xt equal to e to the power lambda t into V, when we assume that as a solution of the equation x dot equal to Ax, then we arrive at the equation whereby we need to find the we need to find the eigenvectors and eigenvalues of the matrix A. So, when you find corresponding to the eigenvalue lambda j Bj as an eigenvector, then corresponding to that xjt will be a solution of equation 1. If A has n linearly independent eigenvectors B1, B2, Bn with eigenvalues lambda 1, lambda 2, lambda n respectively. Now, note here that lambda 1, lambda 2, lambda n need not be distinct. When lambda 1, lambda 2, lambda n are all distinct eigenvalues, we shall see that their corresponding eigenvectors are linearly independent. But even in case where lambda 1, lambda 2, lambda n are not all distinct, we might have n linearly independent eigenvectors. So, so that is why suppose B1, B2, Bn are n linearly independent eigenvectors of the matrix A corresponding to the eigenvalues lambda 1, lambda 2, lambda n respectively, which need not be distinct, then xjt equal to ejt into bj, j equal to 1, 2 and so on up to n are n linearly independent solutions of the vector differential equation 1, that is x dot equal to Ax. Now, this follows from the theorem on test for linear independence. If you remember, we did in the last lecture, we said that the k solutions x1 t, x2 t, xkt, x1 t, x2 t, xkt, the k solutions of x dot equal to Ax are linearly independent if and only if x1 t naught, x2 t naught and so on xk t naught are linearly independent vectors for some suitable value of t equal to t naught. So, here if you choose t equal to t naught to be 0, then we see that xjt, okay, xjt equal to e to xjt equal to vj, and vj b1, b2, bn are linearly independent. So, xjt for j equal to 1, xj0 for j equal to 1, 2 and so on up to n are linearly independent, and therefore, the solutions xjt for j equal to 1, 2 and so on up to n are linearly independent, and therefore, a general solution of the vector differential equation x dot t equal to Axt can be written as xt equal to C1 e to the power lambda 1 t into V1, C2 e to the power lambda t into V2 and so on Cn e to the power lambda n t into Vn, which is called the general solution. Now, if A has n distinct real eigenvalues lambda 1, lambda 2, lambda n with eigenvectors b1, b2, bn, then the situation is the simplest, because the eigenvectors b1, b2, bn are linearly independent as shown by the following theorem. Any k eigenvectors b1, b2, bk of A with distinct eigenvalues lambda 1, lambda 2 and so on lambda k respectively are linearly independent. Let us prove this theorem. We shall prove this theorem by induction on k. for k equal to 1, the eigenvector b1 is clearly linearly independent, because if you take constant times b1 equal to 0, then this implies c equal to 0, because b1 is an eigenvector. So, b1 is not equal to 0. So, for k equal to 1, the theorem is true. The theorem is true for k equal to 1. For k equal to 1, we have seen whenever we consider c v1 equal to 0, we get c equal to 0, and so v1 is linearly independent. Now, let us assume that the result is true for k equal to j. Okay. So, assume that which means that any set of j eigenvectors of A corresponding to distinct eigenvalues, corresponding to j distinct eigenvalues is linearly independent. So, okay. So, now and then we shall show it for j plus 1. Okay. We shall show that if you consider j plus 1 eigenvectors corresponding to distinct j plus 1 distinct eigenvalues, then they are linearly independent. So, let us assume that let b1 b2 b2 bj plus 1 be j plus 1 eigenvectors of A corresponding to j plus 1 distinct eigenvalues lambda 1 be right here, lambda 1 lambda 2 lambda j plus 1 respectively. Okay. Now, in order to prove that b1 b2 bj plus 1 are linearly independent, let us consider the equation c1 b1 plus c2 b2 and so on cj plus 1 bj plus 1 equal to 0 vector, okay, where c1 c2 cj plus 1 are scalars. Now, if we want to show that b1 b2 bj plus 1 are linearly independent, then we shall have to show that c1 c2 cj plus 1 all are zeros. Now, what we do is, let us operate on this equation by the matrix A. So, when we operate by A, we get this. Now, A matrix and this is 0 vector. So, we get 0 vector here, okay, and left hand side using the properties of matrices, we have C1 times AB1 plus C2 AB2 and so on Cj plus 1 is Abj plus 1 equal to 0. And since b1 b2 bj plus 1 are eigenvectors of A corresponding to eigenvalues lambda 1 lambda 2 lambda j plus 1, ab1 will be lambda 1 b1, this will be lambda 2 b2 and so on, this will be cj plus this will be lambda j plus 1 bj plus 1 equal to 0. Now, what we do is, let us take it as equation 1 be multiplied by lambda 1, okay, we multiply equation 1 by lambda 1 and then subtract from 2. So, multiplying 1 by lambda 1 and then subtracting from 2. What we notice is, let me write here, we get, okay, so C1 lambda 1 B1 will cancel with C1 lambda 1 B1 and we will get C2 lambda 2 minus lambda 1 into B2 plus C3 lambda 3 minus lambda 1 into B3 and so on, Cj plus 1 lambda j plus 1 minus lambda 1 into Bj plus 1 equal to 0 vector. Now, B2, B3, Bj plus 1 are j eigenvectors of A corresponding to the distinct eigenvalues lambda 2, lambda 3, lambda j plus 1 respectively. Okay. So, by our hypothesis, since we have assumed that the result is true for j, k equal to j, okay, it follows that B2, B3, Bj plus 1 are linearly independent. So, we have C2 lambda 2 minus lambda 1 equal to 0, C3 lambda 3 minus lambda 1 equal to 0 and so on, Cj plus 1 lambda j plus 1 minus lambda 1 equal to 0. Now, we have assumed lambda 1, lambda 2, lambda j plus 1 to be distinct eigenvalues. So, lambda 1 is not equal to lambda 2, lambda 1 is not equal to lambda 3, lambda 1 is not equal to lambda j plus 1. So, what we get here? We get here C2, since lambda 1, lambda 2, lambda j plus 1 are distinct, we get C2, C3 and so on, Cj plus 1 equal to 0. Now, still we have to show that C1 is 0. So, what we do, we go back to the equation 1. Okay. We go to the equation 1, put here C2 equal to 0, C3 equal to 0, Cj plus 1 equal to 0. So, then equation 1 gives us C1 B1 equal to 0, and we know that since B1 is non-zero eigenvector, C1 B1 equal to 0 implies C1 equal to 0. So, thus C1 equal to C2 and so on, Cj plus 1 equal to 0, which implies that the result is true for k equal to j plus 1. So, by mathematical induction on k, the result holds for any k. So, this is the proof of this result. Now, let us take the example. Suppose we have the vector differential equation x dot equal to Ax, where A is the 3 by 3 matrix 1 minus 1 4, 3 2 minus 1, 2 1 minus 1. Then we want to solve this vector differential equation using the method of eigenvalues eigenvector. So, what we will do? We will find the characteristic equation. We write the characteristic equation as determinant of A minus lambda I equal to 0, which gives us from the diagonal elements of A we subtract lambda. So, 1 minus lambda minus 1 4 3 2 minus lambda minus 1 2 1 minus 1 minus lambda, this determinant equal to 0. Then we expand this determinant. Okay, what we will get? 1 minus lambda times 2 minus lambda into minus 1 minus lambda and then we get plus 1. Okay, then we get minus of this, so plus 1, and then we have 3 into minus 1 minus lambda, and then plus 2, and then we get 4 times 3 minus 2 into 2 minus lambda, that is 4 minus 2 lambda. Okay, we can then simplify this equation. We will get a cubic equation in lambda. So, this will give us a cubic equation in lambda. We can easily solve the cubic equation in lambda. It will turn out that the roots of this the roots are are 1, 3, minus 2. Okay. So, the eigenvalues of A are lambda 1 equal to 1, lambda 2 equal to 3, and lambda 3 equal to minus 2. Now, what we will do corresponding to the eigenvalue lambda 1 equal to 1, let us find the eigenvector for of the matrix A. Okay. So, we have to solve the equation A minus lambda I b equal to 0. Okay. Lambda is equal to 1 here. So, we get A minus I b equal to 0. Now, A minus I means from the matrix A we subtract the identity matrix. So, when you subtract the identity matrix from here, the diagonal elements will be subtracted by 1 each. So, we get 0 minus 1 4, that is the first row, 0 minus 1 4, then we get 3 1 minus 1, and then we get 2 1 minus 2. Let us say V vector B is B1 B2 B3, right hand side is 0 vector 0 vector. So, now we have to solve this equation. So, the first we have a system of 3 equations here, homogeneous system. So, first equation gives you B1 into 0 minus B2 plus 4 B3 equal to 0, that is to say B2 equal to 4 B3. Second equation is 3 B1 plus B2 minus B3 equal to 0, and so we can put the value of B2 here. So, this gives us 3 B1, B2 is 4 B3. So, 4 B3 minus B3 is 3 B3, 3 B3 equal to 0, which gives us B1 equal to minus B3. Okay. So, now we need not solve the third equation 2 B1 plus B2 minus 2 B3 equal to 0, because the 3 equations are not linearly independent. One equation is always a 0 equation, it is a linear combination of the other 2. This is because the determinant of A minus lambda equal to 0. So, so what we do is let us write the vector V then. The vector V is B1 B2 B3, B1 B2 B3, B1 is minus B3, B2 is 4 B3, and B3 is arbitrary. So, I can write it as B3 times minus 1 4 1. Okay. Now, choosing B3 equal to any non-zero scalar value we can choose for V3. So, let us choose the convenient value B3 equal to 1. Taking B3 equal to 1, we get B1, we get V1, we get the vector V, B is equal to minus 1 4 1. Okay. So, this is vector V1 corresponding to eigenvalue lambda 1, and therefore, one solution of the vector differential equation we can find for the eigenvalue lambda 1 and eigenvector B1. It is e to the power lambda 1 t, lambda 1 t means e to the power t, and then B1 minus 1 4 1. So, this is one solution of the given differential equation. Now similarly we can find for the eigen value lambda 2 equal to 3, for the eigenvalue lambda 2 equal to 3, let us find the eigenvector. So for lambda 2 equal to 3, we have to solve a minus 3i b equal to 0. A minus 3i, if you find a minus 3i will be, you subtract 3 from the diagonal elements of the matrix A. So when you subtract 3 from here, you get minus 2 minus 1 4. So you get minus 2 minus 1 4, and then you have here 3 minus 1 minus 1, and then here you have 2 1 minus 4. Now we can see here first equation is minus 2b1 plus minus 2b1 minus b2 plus 4b3 equal to 0, and third equation is just minus times the first equation, because it is 2b1 plus b2 minus 4b3 equal to 0. So we can consider only first two equations, that is first two rows, minus 2 minus 1 4, 3 minus 1 minus 1, and the two equations in 3 unknowns b1 b2 b3 can be solved, okay, and we will get the eigenvector, an eigenvector for lambda 2 equal to 3 as b2, that is 1 2 1, okay, and the corresponding solution will then be equal to x2 t equal to e to the power lambda 2 t, that is e to power 3 t into 1 to 1. And for lambda 3 equal to minus 2, similarly we can find for lambda 3 equal to minus 2, we need to solve the equation a minus lambda I, that is a plus 2i b equal to 0. So to the matrix A, we add 2 times the identity matrix, that means we add in the diagonal elements of A 2, and then the matrix that we get that will be a plus 2i. So a plus 2i to b equal to 0 can be solved, and we get b3 equal to minus 1 1 1. So the third solution is then given by x3 t equal to e to the power minus 2t and then minus 1 1 1. Okay. The solutions of the given system is then of the form xt equal to c1 e to the power t. Okay. So c1 times x1 t, c2 times x2 t, c3 times x3 t. So we get if you multiply these c1 e to the power t, c2 e to the power 3 t, c3 e to the power minus 2 t to these 3 column vectors, and then add, what you get is this minus c1 e to the power t plus c2 e to the power 3 t minus c3 e to the power minus 2 t, and then 4 c1 e to the power t plus 2 c2 e to the power 3 t plus c3 e to the power minus 2 t, and then you get here the third component as c1 e to the power t plus c2 e to the power 3 t plus c3 e to the power minus 2 t. So this is the general solution of the given vector differential equation. Now let us take another problem. This is an initial value problem. Here we are given the vector differential equation x dot equal to ax, and we are also given an initial condition, that is at x t equal to 0, x is equal to 0 1. Okay. So again we shall write the vector differential equation here. We shall write the characteristic equation here, 1 minus lambda 12 3 1 minus lambda equal to 0, and this will give you a quadratic equation in lambda, 1 minus lambda whole square minus 36 equal to 0. So you can say that 1 minus lambda is equal to plus minus 6. Okay. So taking 6, when you take 6 here, then we get lambda equal to 1 minus 6, so minus 5. Okay. And when you take minus 6 here, then 1 minus lambda equal to minus 6 gives you lambda equal to 7. So we get 2 eigenvalues of lambda, 7 and minus 5, and they are both real and distinct. So corresponding eigenvectors will be linearly independent. So for lambda 1 equal to 7, it turns out that b1 is 2 1. So x1 t is e to the power 7t into 2 1, and lambda 2 equal to minus 5 gives you b2 equal to minus 2 1. So x2 equal to e to the power minus 5t minus 2t minus 2 1. Okay. So the general solution is what? Xt equal to c1 x1t plus C2 x2t, and we then use the initial condition, that is the value of x at t equal to 0, which is given as 0 1. So, if you do that, okay, what you get is this, this will be x0, put t equal to 0 here. So, x0 equal to C1 x10 plus C2 x20, okay. X0 is given to be 0 1. So, 0 1 equal to C1 times x10 you can find from here. When you put t equal to 0, you get 2 1 here, and then you get C2 times x20. When you put t equal to 0, you get minus 2 1, okay. So, this gives you 2 C1 minus 2 C2 equal to 0, and then C1 plus C2 equal to 1. So, it is clear C1 is equal to C2, and so 2 C1 equal to C1 plus C2 is equal to 1. So, this gives you C1 C2 equal to half each, okay. So, put the value half here. So, then xt is equal to half, xt is equal to half x1t plus x2t. So, this is the particular solution of the in given initial value problem. So, xt turns out to be e to the power 7t minus e to the power minus 5t, half e to the power 7t plus half e to the power minus 5t. That is all for this lecture. Thank you very much for your attention.